Yeah, hi everyone. My name is Rubenzahl. I'm a finishing grad student at Caltech. I'm very excited to talk about the KPF Solar Calibrator, a project that's a big part of my PhD thesis that I've been working on with Sam Halverson at JPL, Josh Wallawinder and Grant Hill at Keck, and my advisor at Caltech, Andrew Howard, as well as many people at Keck Observatory whose contributions, both large and small, were critical for getting SoCal on the roof of Keck and working. So just wanted to give a special mahalo to everyone who I've circled in this picture and listed above, and anyone else who I may have missed who contributed to SoCal. So to kick things off, I wanted to show the entire history of exoplanet radial velocity history on one plot. So this is starting in 1995 with the very first radial velocity exoplanet, 51 Peg B, which has a 50 meter per second or so radial velocity semi-amplitude. And since then, as instruments got more precise and more new instruments came online, we were able to discover and measure the masses of smaller and smaller planets. But this trend has seemed to have bottomed out since about 2010 or so. We haven't really discovered any planets smaller than a half a meter per second to 1 meter per second. And that's despite having a number of facilities that are online now that work, that have sub-meter per second capabilities. We still have a ways to go to get to the 9 centimeter per second line, which is an Earth mass planet around a sun-like star at 1 AU. This is, of course, because of this fun little thing called stellar activity. This is a name for a wide range of physical processes on stars that can create noise in the radial velocities that we measure across a wide range of timescales, from pressure mode oscillations or P modes in this, literally the star pulsating. In the sun, it's about a meter per second every 5.5 minutes. Granulation on hours to days timescales, spots or other surface inhomogeneities that will modulate the velocities on the rotation period of the star, which could be weeks to months. And then, of course, on the sun, there's this 11-year activity cycle where sometimes there's many sunspots, sometimes there's no sunspots. These can all mimic planet signals. They can mask true planet signals. And importantly, they're all bigger than the measurement precisions of instruments like the Keck Planet Finder. And so to really utilize the true precision of KPF and measure small planets, we need to be able to understand stellar activity and hopefully overcome it. So it might be no surprise then that all of the current and next generation EPRV facilities are including mean solar feeds to measure radial velocities on the sun just like we would any other star. And this might make sense. Is Mike Brown in the room? Or do I need to put an asterisk on this? We know all of the planets that orbit the sun. And what that means is it's the only star in the universe you can remove their contribution from your measured velocities, and what you're left with is variability from your instrument, which you of course want to know and understand, or variability due to the sun, due to solar activity. And that will be the same across all of these facilities. And then the differences would be because each of the instrument has their own unique noise properties. And one special thing to note here is that only the NUID solar feed, which came online a couple years ago, and KPF SoCal will be making data available immediately, public to everyone. KPF SoCal data is on COA. And so you can do these kinds of cross comparisons between these different facilities and better understand our instruments and solar activity. So SoCal, just like all of these other solar feeds, has a pretty simple optical design because we can't point Keck at the sun. We make do with the 3-inch lens that we point at the sun that focuses the sunlight into this 2-inch diameter hollow integrating sphere. The light bounces around about 1,000 times before it randomly lands on the optical fiber and gets funneled all the way into the basement and injected into KPF, just like KPF would see a star through the Keck telescope. This whole process, you lose about a factor of 200,000 in throughput, but it's the sun. So it effectively turns the sun into pointing Keck at Vega, is roughly the same. So SoCal has been in many places since we first received delivery of it in March 2020. And then everything, of course, shut down. So initial testing I did on a pop-up card table that I put an optical breadboard on in my apartment, which has a smaller square footage than the primary mirror of Keck. So that was a fun year. Last year, we moved to just up the road to the roof of the Space Sciences Lab at UC Berkeley, where KPF was being assembled and tested. And since this time last year, which is why I was not at the Keck Science Meeting last year, despite it being at Caltech, I was a Keck visiting scholar working with Josh Wallowinder to develop this control software and do the initial hardware testing and integration at Keck. So here's a few pictures from our installation in December, where we dug a big hole, or rather, an excavator dug a big hole, and I posed in it with a shovel. Buried a heavy steel plate and assembled the weatherproof enclosure on top, and then posed like Doc Brown in Back to the Future, plugging it in for the first time. And 2 days after we took that photo, big winter storms hit the summit. Winds of over 100 miles an hour, heavy snow and ice, basically turned SoCal into an ice cube through well into March. And when we came back in April, the enclosure did its job. It didn't blow away, and it kept everything nice and dry. We could run our fibers from the roof down to the basement, connect with KPF, assemble all those optics on the solar tracker, and took our very first, oh no, this was a birthday emoji, because it, April 25th is also my birthday. So we happened to get our first RV time series, so now SoCal and I share the same birthday. And here's the one of the first light spectra. You can find the sodium doublet in there somewhere. So each day now, the enclosure will autonomously open around when the morning calibration sequence for KPF ends, near 9 in the morning. The tracker will autonomously, it has a GPS connectivity, so it'll go where it thinks the sun is, and then it has an active guide sensor on the far arm, down under here, to lock onto the sun and track on it throughout the day. Also on this arm is a thing called a pyrheliometer that just measures the solar irradiance, so watts per square meter. We basically use that as a glorified cloud detector. And then the other arm with the bigger piece is the lens and integrating sphere that I was mentioning before. So I mentioned as part of my time at NYMEA, as a visiting scholar, I worked with Josh to develop the software to do a sort of autonomous control loop, where we basically just define a number of states where, say, the enclosure is open and we're guiding, and then define specific transitions to move the instrument between all of those states. And that ties all together into one big operations loop that we can catch errors and hopefully gracefully recover back into the state that it came from, with the idea of making everything as requires little human interference as possible, and it can just run itself. So it is the Keck Science Meeting, so I should show some data. So far, we have nearly 14,000 radial velocities. In 5-second exposures, we reach signal to noise of about 1,300. Most of this data is in the standard readout mode, so that's 47 seconds between exposures, but we have a number of days, and we plan to operate long-term using the fast readout mode of KPF, which is only 16 seconds, so that gives us basically a 20-second cadence. And all of the data is processed using the same public data reduction pipeline that is used for nighttime observations of stars. I mentioned the pyrheliometer, so we use that as a cloud detector, which is important because the sun is a resolved disk, unlike stars, which are points. So if a cloud passes in front of the sun, it might block a portion of the rotating solar profile and can create RV variations of kilometers per second. So I have this code that just sifts through. If it's a clear day, you have a nice flat irradiance time series, and the RVs are very well behaved. If it's cloudy, there's these big dips, so the code will catch that and then tell you which RVs happened in that time and just kind of throw them out. So we keep only the high-quality solar data. Here's some of the data we took in the fast readout mode. So this is at that 20-second cadence. Showing separately the green and red CCD RVs derived from the green and red cameras separately. You can really clearly see the 5.5-minute oscillation periods of the sun, very nicely traced out. And if we combine those two into a single radial velocity and then bin over the P-mode oscillations, you get an RMS over this couple hours time series of about 26 centimeters per second, which is the same as the single measurement precision we get in just one of those 5-second exposures. So this is very encouraging, showing the KPF is very stable, at least on these short time scales. On these days where we have very little instrumental drift, the sun was pretty quiet, so the only thing that was moving was the spectrometer. Lastly, because we have a couple hours of overlap with NUID at Kitt Peak in Arizona, and the NUID data is public immediately, we can go and compare our data to theirs and find we're seeing the same sun. When I first made this plot, I was misplotting like barycentric Julian date and just Julian date. And when I flipped that and replotted it, they just lined right up, and it was very beautiful to see. So taking the difference between these, we get a very nice residual radial velocities with an RMS that's comparable to the combined measurement precisions of both instruments. So again, this is good news for KPF and for NUID, that both instruments, at least here, are seeing the same variability from the sun, and there's very little internal disagreement. And we have lots of days that show where the skies happen to be clear at both sites, and have lots of good comparisons we can do. And very interesting comparisons we can do are the times where things don't agree, like up here, which will require more investigation, but might reveal something about one or the two instruments. So to wrap everything up, we have 13,000 radial velocities with 1 million more well on the way. I only say that half jokingly. In the fast readout scheme, in a 6-hour day, it's about 1,000 spectra a day. So in 3 or so years, we'll be getting close to that. We've passed the 30-year total of high-res in photons collected in about 3 weeks. We're diagnosing problems with KPF and solving them. The solar data have been critical in just having a nice standard of an actual star where we know what's going on and can do many different kinds of tests. We see very superb agreement with NUID, and coming soon will be analysis on longer timescales once the KPF pipeline is better stitching together wavelength solutions across multiple days. So with that, I'll take questions.